So the premise here is that you think about. Okay, you guys ready to start? Okay, you ready to start? Okay, you ready to start? Okay, you ready to start? Zach, can you whisper? All right, so the premise on the can is think about not a hollow can, but a solid can, right? Solid material, just all filled up in there. And so then the quantity would be volume. And then if you let that volume just grow, or that can grow, that solid can grow a little bit bigger into a slightly bigger solid can. So now it's just a little bit bigger in all dimensions, like this. And so you have a solid can, and then you let it grow, and you have another solid can, all filled with metal. So that dV, that the change in volume, then you can imagine would be a model for a hollow tin can. Do you see that? Does that make sense? That's what the premise of that problem is. That dV then models a shell, or a can type thing. So then in order to like estimate the amount of material of the can, you're using dV, right? A little change in volume of a solid can would be like the same as the material of a hollow can. Can you picture that? So that's what that is. And so, and they kind of set it up for you. They said dV equals something times dH plus something times dr. Well, we know that's exactly our differential formula. In order to get, and what are those things? That would be, what would this be? Just not what is the expression, but what would be multiplied by dH to get the differential dV? The partial derivative of v with respect to h, right? And then this would be the partial derivative of v with respect to r. So we need v as a function of h and r to get those partial derivatives and to set up this differential. So what is v as a function of h and r? Pi r squared h. So we can get our partial derivatives from our v formula, and then that will give us what we need to write the differential of volume. And then that differential of volume is like the amount of material of a hollow can, because it's like the increase in size of a solid can. So that's just an overview of that one. So I couldn't look at the web work per se, but that's just an overview of that. All right, yeah.
So when you're setting up, like when you plug in the values for dr and dh, for dh, the answer, like it gave you like how much the width was,
right,
on each side, and you had to double that because it was on both sides, correct?
No, you wouldn't have to double on both sides because the radius is just increasing the radius by dr gives it the radius increased all the way around. But increasing dh, there's two places where dh occurs, but dr there's only one, and it takes care of all the way around. Yeah. So I think they kind of gave you a little hint there too. They're like, be careful on this, right? Okay. Right. So dh then is gonna have the effect of both the top and the bottom, whereas dr is just the one change in radius. Okay, anything else? Okay, very good. So let's just review we're going to talk about second partial derivatives today. So let's just review first partial derivative. So I've got this multivariable function here and a point on it. So I just want you to tell me what you can tell me about the first partial with respect. It's a little bit too angled. Let's try this. Tell me what you can tell me about the first partial with respect to x and the first partial with respect to y at that point that I've highlighted there on the surface. So what's the premise of the first partial with respect to x? There we go, let's try that. So when you're talking about the first partial with respect to x, that's a rate of change, so what's the premise behind that? It's the rate of change when what? Yeah?
Rate of change of z as x changes y small.
Right, so we're going to just change, let x change. Keep y fixed, just let x change, and then see what z does, and then we'll have a rate of change in that direction. So what do you think the rate of change is in this case? What can you say about it? So here I am showing you holding y constant. And so by that plane, right, that's the y value of the plane of that point. So the intersection of our surface and that plane form a trace, right? Do you see the trace? That's a good view of it. So here's x going to the right here, y going back. And so the intersection of the constant y value and our surface forms a trace. And so that along that trace is what pertains to the rate of change or the first partial with respect to x. So what can you say about the first partial with respect to x? Partial derivative with respect to x. Looking at that trace. He wants negative. Agree with that? Yeah, because if you change x a little bit, which is to the right, if you go to the right a little bit, z will go down. Right? So along that trace for the constant y value, we see our first partial with respect to x is negative. What about y? What about the partial derivative with respect to y? That would be holding x constant and looking at that trace, right? So now I'm holding x constant, and by showing that plane, there's a trace then along that surface, and along that trace gives us an image or a picture of the partial derivative with respect to y. What would you say now? Positive, right? Little change in y means you go up. Okay, so that's just review. So now let's talk about second partial derivatives. Second partial derivatives. Second order partial derivatives. And I think you've already calculated some from web work. We haven't talked about them yet, but you did whatever research you needed to do just to calculate those. That's not too bad. So, shoot. That'll do it. All right. So, the second ordered partial derivative with respect to x is the notation would be like fxx, or it'd be the derivative of f of x with respect to x. The partial derivative of the partial derivative with respect to x with respect to x. That's just fxx. What does it reveal about the function? What does it reveal about the function then? If it's the derivative with respect to x of the partial derivative, then what would it reveal about the function? It's not on your smartphone. It is somewhere, but not on the screen that you're looking at. Yeah. Yeah, right. The rate of change of the rate, right? So it'd be like the rate of change of the rate. So how the rate of change of z with respect to x is changing with respect to x. Okay, and so if we applied our mantra to this, right? What's our mantra for rate of change? So what would we say? So how would you describe the meaning of that with a sentence? So think about that and then pair up and try to tell the person next to you. Remember what we said about what is the meaning of rate of change. So now it's the rate of change of this, the partial of f with respect to x. So what would that mean? What would that mean? Go. So think and talk. If you're getting tongue-tied, you're on the right track, right? If you're getting tongue-tied, you're on the right track.
It's like gamma stocks. Right. It's like, yeah, it's the change.
Okay, Gavin back there in the corner. What do you think? So, how could you describe using our theme about rate of change? How could you describe what this rate of change is? Right, and so what does that mean, right? That's exactly what it is. What does that mean? How do we make meaning out of that? Jacob, right next to him. Did you? Good start for a small change in x. Right? Gives you, what does it give you? No. Okay, but yeah, so it's something like that. All right, anyone want to try it? Any volunteers? Matt, Dominic.
I was going to say for small change in x, there is a change of the rate of change for that change in x.
Right, and how do we find that change in the rate of change? Yeah, Alex, what are you going to say? Right. Right. So given a small change in x, the change in the first derivative with respect to x, how much the first derivative changes equals to our second derivative times the change in x, right? So given any small change in x, how much the first derivative changes with respect to x is going to be that second order partial times your change in x. Okay, suppose that the second order partial with respect to x is greater than 0. What can you conclude? What does it mean that if the second partial is greater than 0? Okay, more. That's true. Can you say anything more than that? Right, so that means so if the second partial is positive, that means the first order partial is increasing. So what does it mean that the partial with respect to x is increasing? That's what this means. If your second partial is greater than 0, then your first partial derivative, partial with respect to x, is increasing. No, that's the function. The function is increasing at a decreasing rate. The derivative, the partial with respect to x, is just increasing, right? What does it mean that the partial with respect to x is increasing? Yeah. Okay, so for the derivative to increase, it could be getting what? Less negative or more positive. Right, so if your second partial is positive, that means your changes in the first derivative are positive, which means that first derivative is increasing. And when that first derivative increases, so what does that mean for a graph? So now we're just looking at the zx plane. What does that mean for the graph if the first derivative is increasing? Yeah, Justin. Right, so it could be watch. Your partial with respect to first derivative is getting less negative, so that's what it means to get less negative. So you're decreasing rapidly, then decreasing less rapidly, and less rapidly, and less rapidly. That's one way that your first derivative could be increasing. And the other way is your first derivative could be getting more positive, right? One more time, because it's so cool. All right, first derivative getting less negative. So decreasing sharply, but decreasing less sharply as you increase x, or the first derivative getting more positive. That's what we mean by the partial derivative increasing, and so then the graph is turning up. Whether it could be heading down or heading up, but it's always turning up, right? It's turning up. That derivative is increasing. All right, so what does it mean for, or concave up, right? So if the graph is turning up, then we could say that's concave up. All right, what about if the second partial derivative is less than 0? What does that tell us about the first derivative? It means that changes in the first derivative are negative, which means that the first derivative is decreasing, right? And how can a graph be decreasing, or a function be decreasing? Sorry, the derivative. How is the rate of change decreasing? Two ways it could be decreasing. The rate of change could be getting less positive, right? So increasing sharply, and then increasing less sharply, and then increasing more slowly. So that's a way that your first derivative could be decreasing, or first derivative could be getting more negative, right? Decreasing faster and faster. And then that means that the graph is turning down, and we call that concave down. So the first derivative tells us if the function is increasing or decreasing. The second derivative tells us if the rate of change is increasing or decreasing. So that's what derivatives always tell us, if the original function is increasing or decreasing. So if it's the second derivative, it's telling us whether the first derivative is increasing or decreasing. Okay, so let's practice. Back on this graph. So let's go to this one. I'll do this one first. Okay, so what do you think? So we said that the first partial with respect to x was what, positive or negative? First partial with respect to x, positive or negative? Negative, because z is decreasing, right? The function is decreasing. Now what about the second partial with respect to x? Positive or negative? So as you increase x, is the rate of change decreasing or increasing? Try it from looking at it from this way. I think that's the best view right there. X is to the right. So as x increases to the right, is the rate of change increasing or decreasing? Here it comes like this, right? It's coming like this. What do you think? Decreasing, right? Decreasing. Because the function is decreasing, but the rate is becoming more negative, right? The rate is becoming more negative through there. So both the first and the second derivative with respect to x here are negative. Stop me if you don't see that. Do you see that? Okay, what about with respect to y? First derivative, what did we say? People are saying positive. Agree with that? Because the function itself is increasing, right? If the first derivative is positive, the function increases. Second derivative, he wants negative. Agree with that? Second derivative is negative. Because it's increasing, but increasing at a slower rate, right? It's increasing at a slower rate. So the second derivative is negative here. The first derivative is positive. Okay, let's do it again. if I can see that. Is that 113.2? Can you read it? Yes. Oh, this is good. I can read that. I want 2.84. Really? Okay, I guess that's what I want here. All right, so ooh, it's not happy. There we go. All right, so at this point, let me put the y on it. So we'll do x first. Okay, do x first, and I want you to do the partial with respect to x and the second partial with respect to x first and second at the point in question there. Go. Okay, first partial with respect to x. Alyssa, what do you think? Because? Right, if you move a little bit in the x direction, you go down, right? That's the first derivative. And now what about the second derivative with respect to x? So you're asking about how the first derivative is changing. What do you think? Yeah? Increasing? I was going for something different than that. Maybe like that. That's pretty good. Okay, yeah, so you think it was what? So if it were here, I would definitely go with increasing, but I was going for something different on this. Yeah. Yeah, so I was going for where actually the first derivative is not changing. So maybe I might have not done a great job, but that's what I was going for. So if you were back for lower x values, your first derivative would be negative, and then for greater x values, your first derivative would be positive because your rate is increasing. So I was going right for the middle point of that, where actually for a moment there, the rate of change is not changing. The rate of so it's like linear for a moment, right? There's no change in the rate. So I was going for second derivative of 0. All right, so now I'll do with respect to y. Okay, so now okay, so kind of read my mind a little bit. I might not have it just in the right place, but kind of try to read my mind with that. Okay, so now talk about that. This is partials with respect to y, the first and second derivative. And I'm going to start taking time notes. Kevin, what'd you think? First partial with respect to y. He wants it to be 0. First partial with respect to y is 0. Because? So yeah, so for a change in y, we're not going to really see much increase or decrease because it's at the minimum, right? What about the second partial with respect to y? Think about that. Yeah, sure. But so then what is the second partial? Second partial is positive. Agree? Yeah, so even though we're at the bottom, all through here, what? The rate of change is it's increasing, right? Getting less negative switching to getting more positive, but that doesn't mean it's 0 at the bottom. It's continually increasing. That second derivative, the first derivative is increasing the whole way through, so that second derivative is positive. Everyone agree with that? Does that make sense? Okay, what's next? $170.8. And 1.72. Right there. So we'll do, this is this for analyzing the partial with respect to y or x? Y, I'm holding x constant, right? You're looking at the trace of the intersection of a constant x value with the surface. Go. Partial with respect to y. Okay, what do we think? Pierce, what's the first derivative? What do you say about the first derivative here? First derivative 0, why? What's that? What's it? So what function value is not increasing or decreasing? First derivative? I think the first derivative is either increasing or decreasing. So what is it that's not changing, not increasing or decreasing, that results in the first derivative being 0? What's that? Yeah, the function, the z value, right? So it's just the z value, the value of the function. It's not, doesn't change for a change in y, and so that's why we have our first derivative is 0. Second derivative. Corinne? Because? Okay, because the rate is doing what there? Getting less positive or more negative. So the rate of change is decreasing all through there. So our second derivative is negative, okay? With respect to x now. Okay, so there's the trace here. First derivative with respect to x. Positive, negative, or 0? First derivative. X is to the left now, right? So we're looking down the y-axis. X is to the left. So first derivative, positive, negative, or 0? Negative, right? For an increase in x to the left, z goes down, right? Second derivative with respect to x. Positive, negative, or 0? Positive, negative, or 0? What do you guys think? Negative, right? The rate is getting more negative as you increase x. It's shot like a little bit negative, but then it's getting more and more negative through that point. Questions? Does it make sense? All right, next one. 149. Okay, 104, 1.72. All right, right there. First derivative with respect to x. First derivative with respect to x is 0. Z doesn't change for a small change in x. First derivative with respect to y. Also 0. And as a result, we have what? Both the first partials with respect to x and y are 0. And therefore, the directional derivative would be 0, no matter what direction you went, right? So if you got both partials equal to 0, then every value of the directional derivative would be 0. And so no matter which way you go, you're going to basically stay at the same z level for a very small change. And so here we have, this is a local maximum, right? So where else in this picture do we have both first derivatives equaling 0? At the very bottom, right? So where's that? Ooh, right there, right? So there's another place at the very bottom. All derivatives, every directional derivative, including both partials, equals 0. So we have a local minimum there, right? And so what about the second derivatives there? What about the second derivatives there? Partial with respect to both positive, right? Both positive at the bottom, because no matter what way you go, no matter which way you go, your rate is increasing, right? Becoming less negative, more positive at the bottom. Okay, anywhere else where both derivatives are 0? Yeah?
There's another local.
There's another local min. Back there somewhere around there. Anywhere else?
Or in that value.
Okay, right. So that is at 104. There's another place here that has both partials equal to 0. Get it? Please. 104 and 2.24. Do you see that both partials there are 0 as well? Is it a local max or a local minimum? Is it a max or a min?
It's tough. It's
So what is it? Is it a local max or a local min? Oh, that's not the right place, is it? But you know what I'm trying to do. You know where I'm trying to go. So I'm right there. Okay? So it depends which way you're going, right? So if you're traveling this way, along this diagonal here, you got a local max. But if you're traveling this way, across the screen like this, it'd be a local min. Okay? So just because both partial derivatives are 0 doesn't mean you necessarily have a local max or a local min. You might have one of these. It's called a saddle point, right? So it looks like a saddle. You could sit in it, right? You could sit in that. But your partial derivatives are 0 because if you make a little change in any direction, you're staying at about the same z value. It's just in some directions, if you keep going, you go down. And in other directions, if you keep going, you go up, right? So it's not like you always go down or always go up. So this is what's called a saddle point. So let's talk about local max, local min, and saddle points. So a critical point is any point such that both first partials are 0. That's the last example we looked at. So both partial derivatives are 0. F of x at AB equals f of x at AB equals 0. So we looked at the three possibilities for that. Local max, local min, or saddle point. So to identify what you have, if you don't have a picture, you just have the function, just like the formula, and you're trying to figure out what you have, there's this thing called the discriminant. Okay, the discriminant is this. It's the second partial with respect to x times the second partial with respect to y minus the product of the mixed partials. But the mixed partials are equal by a thing called Clause's theorem. We didn't take the time to look at that. but those are equal, so you can just pick one of them and square it, okay? So this is the discriminant. You take the product of the second partials with respect to x and y, subtract one of your mixed partials squared, and you get a number, all right? So if that thing is greater than 0, you have a local max or min. So if the discriminant is positive, you have a local max or min. Then how can you tell which it is? What would you look at to tell what you have, whether it's local max or min? What's that? The sign on what? So what do we know that's true, say, to local max? So we got both first partials are, so this is always, both first partials are 0. And then we got the discriminant's positive, so what can we look at to figure out? Yeah, Jacob.
If the double partials with x and y are on opposite side, then the discriminant will be negative.
Okay, all right, maybe. Okay, that's not the question I'm asking. If we get the discriminant to be positive, then we know we have a local max or min. Now, how do we tell if it's a local max or a local min? How do we figure that out? Yeah. Right, we're going to look at the second derivative, right? So the second derivative, if it's negative, then what do we mean? We have a decreasing rate of change, and it has to be local max or min. Local max, right? If the second derivatives, if you got a positive discriminant and the second derivatives are positive, what does that mean? It means you're increasing rate, right? So it's getting less negative or more positive. What would you have then? Max or min? Min. Okay, if d is less than 0, then that's a saddle point. And then if it equals 0, there's no conclusion. So you have to investigate it some other way. All right, so this is, we already talked about this. A max, right, is when our second derivative is positive or negative. Second derivative is negative, right? Second derivative is negative because the rate is decreasing. If to know that you have a local max, local min, again, second derivative is increasing, or sorry, derivative is increasing. Derivative is increasing. So the second derivative is positive, and that would correspond to a min. So here's a little, I told you we'd come back to this. So I'll come back to it now. And so I want you to count all maxes, mins, and saddle points in this picture here. Good. All right, so how many maxes, how many mins, how many saddle points? There you go. Yeah. Okay, I'm just kidding, of course. All right, so there's gazillion, right? So we got maxes everywhere, saddle points everywhere, right? Question?
So, I was trying to draw like a 3D model of a saddle. How would you do that?
Draw a saddle?
Yeah.
So the easiest way is do this. Make two like things like that, and then go like that. And that's about the easiest way you can do it.
Okay.
Then you see that you're going your minimum this way, and then your maximum that way. Right there at that point right there. Okay, so how about something more realistic here? How about this one? All right, now this one. Okay, how many maxes, how many mins, how many saddle points? Go. How many maxes, how many mins, how many saddle points? So how many local maxes do you see? I only see one. All right, how many saddle points? Yeah, you can see one there, and one there, and then how many local mins? Just one there. Okay, so here's this function is this function right here. That's highlighted in blue there. So we can do it. So we're going to do the math. Cannot grab onto this. There we go. Trying out loud. Okay. All right, so this function is z equals, or f of xy equals 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. That's the function that you're looking at there with the one local max, one local min, and two saddle points. So how do we find those critical points? We want to find ordered pairs that make both first derivatives equal to 0. So we're going to do the partial with respect to x. That's going to be 6xy plus 0 minus 6x. And the first partial with respect to y is going to be 3x squared plus 3y cubed, check my math, minus 0 minus 6y. Did I do the math right? Okay, so we want to find values of x and y taken together that make both of these 0. So this one will factor out as 6x. We get 6x times y minus 1. And so that's nice because that means in order for the first partial of x to be 0, what has to be true? Either x is 0 or y is 1. So when x is 0, we got to figure out what's y have to be over here in this one to make this one 0, and then we're good, right? So if x equals 0, then their second partial with respect to y is 0 plus 3y cubed minus 6y. Which is, factor out, minus, big. Well, so when x equals 0, we're going to plug in x equals 0 into this one and see what y needs to be to make this 0. Does that make sense? So 3y cubed minus 6y, factor out a 3y, you get y squared minus 2. So when x is 0, what makes this one 0 could be y could be 0 or plus or minus radical 2. 3y squared, thank you. So this should be just y minus 2. Okay, so then it's just 0 and 2. So that gave us two critical points, right? 0, 0 and 0, 2. Are both ordered pairs that make both equations 0. And then the other one that makes the first 0 is y equals 1. And when y equals 1, in the second derivative we get the first partial with respect to y, we get 3x squared plus 3 minus 6. To make that 0, we're going to have 1 or negative 1. So we get two more critical points, 1, 1, and negative 1, 1. The discriminant, so we can make a table for the discriminant. The discriminant, 0, 0, 0, 2, 1, 1, and negative 1, 1. And we could look at what fxx is, what fyy is, what fxy is, and then d for each of those. So I'm just setting up an organized way to determine the discriminant for each one of those critical points. So we would just get the values of each. So we'd have to find the second derivatives, right? Find the second derivatives, all three of those, and then plug these x and y values into those to get the values, and then calculate the discriminant, which would be the first column times the second column minus the third column squared. And then again, if it's greater than 0, you're looking for local max or local min based on the second derivatives. And if d is less than 0, you've got the saddle point. And if d equals 0, then you need something else to make a conclusion about that critical point.
So you don't need to say with a saddle, either it's a max or a min in like the x and the y.
Nope. Just say no, because it's usually angled, right? It's usually angled. So we got our four critical points are going to match up. We're going to end up with two d's that are greater than 0. That's the local max that we saw and the local min. And then two of those d's will be less than 0. Those will be the locations of those saddle points. So now it's just chasing the math out, right? Just doing all the calculations, figuring out what's what. So you should do that. So at home, you should finish this problem and compare it to, I'll give this thing a spin. Compare it to those locations, 0, 0, 0, 2. So there's 0, 2. So we'd expect that to be the max. That looks like 1, 1 here. And then we got the saddle points.